All right. So a couple things off the top. That Connect and Excel assignment are due at the end of the day on Monday, right? So you should have everything you need to get through that first Excel assignment. We've already went over everything, so you should try to start working on that. If you have questions this week, I'll be in my office tomorrow 2 to 4. And then I guess Monday of next week, I'll also be in my office from 2 to 4. So if you have questions, either of those times would be a good time to kind of meet with me and I can kind of help you through it, or send me an email if you're running into problems, and I'll get back to you. That Connect assignment, after the day, you'll be able to get pretty much all the way through it. The last couple of questions, we might not get to until class on Monday. So the last 3 or 4 questions we may not be able to do until after Monday. We'll kind of see what we get to today. If I think that I need to push the due date forward a class period, like to the end of the day on Wednesday, I might do so depending on what we get through today. But I'm going to kind of hold off and see exactly how far we get today before we do that. Okay. And if I do change that, I'll put an announcement on Canvas that the due date is changed. Okay. Also, I think I sent emails to 6 of you, and I already know 2 of you, I think, saw them and registered for the your iClicker. So I think that the error was on my end. I'm using this iClicker Cloud. It's the first semester I've used it. I didn't realize that, I guess for some reason, registering on Canvas, it doesn't register you for the course. So I sent emails to those of you who I wasn't able to sync your name up to your, whatever device you're using. And it had instructions on how to actually register that. So make sure you check your email. Like I said, there should only be 4 left of you, so there shouldn't be many of you. Some of those people may not even be here today. But once we get that, I'll start kind of uploading those courses or iClicker grades. Just I didn't want anyone to freak out. They were getting zeros until I kind of made sure I had everybody able to sync up. Okay, so you'll see those pop up today as well. All right. So if there's no questions, kind of taking care of some of the housekeeping stuff, kind of jumping into materials. Anybody have any questions for me before we go in here? Okay. So hope we had a good break. Kind of left off talking about variance. We also talked about measures of central tendency, mean, median, mode. We'll kind of push it a little bit further to that, right? So sometimes, right, when we are given data, we can't see the original data, and it's only showed to us as group data. So I'll show you a couple of different examples of that today. But you can kind of imagine, I've got an example here. Let's say I was interested in the average fast food sales, right? Well, if all I can see is the data by company, I know that, some small Jim's Burger Shack or somewhere, there's only one location. Well, why should their sales be counted equally as McDonald's, who represents thousands? I don't even know how many stores that would actually represent, right? So I know that I'm only seeing the average sales for McDonald's, and that it represents way more stores. So I want to somehow weight that a little bit more, right? It should carry more weight because it's a couple thousand stores, right, as opposed to just one. So another example I could say I like a little bit better than that is, let's say I was interested in the average income in the US, but I can only see income for each average incomes for every single state, right? There's some database that exists that has every person and their income, right? The IRS has that, but they might put it out to show you the different averages across states. Well, you wouldn't want to simply calculate that mean the same way you would what we talked about before, where you add up the 50 different, incomes you have for each 50 states and then divide by 50, because Delaware's average income represents a much smaller number of people than California's. Right? So what would maybe in that situation I want to use as weights? Different states, population, or working class individuals, or something like that. Right? So if we can only see the data grouped, right, I can only see the average income by state and not the original individual level income, we're going to have to do what we call a weighted mean. Okay, so I had some people asking about this, so I try to show you the formulas, but I try to talk through them and then walk through step by step how we use it in an example, so you don't have to have the formulas memorized. You'll have a formula sheet on the exam, and they're not meant to be I'm never going to ask you to interpret the formula. It's just more so as we use it more and more, hopefully we're getting used to, or kind of being able to use it as a reminder of what the steps are. If you can remember the steps, like, oh, how do I find a weighted mean? It's X, Y, step 1 through 4, that's fine. The formula is just meant to be there as kind of like, okay, we've talked about this summation sign, it always means this, and kind of help you or help remind you about that process. So hopefully after we look at the examples, we'll be able to kind of connect that today. So for a regular mean, we did what? We said this summation sign meant do whatever is to the right of this sign for every single observation, right? I was like 1, 2, 3, all the way to the last observation. Right? So take every single observation's value for X, add them all up, right, for that variable, and then divide by the number of observations or the number of numbers we had. Okay? With a weighted mean, we're still gonna show that it's a mean, right? But we're calculating a different way because the original data is group data. So when we have group data, all this is really saying is go through for every observation and do this. Well, what is this? It's just take that group's value for your X variable, multiply it by the weight for that group, and then add them all up for every single group that you have. Because your groups now are your observations. And then once you do that, divide by the sum of, and I wrote this wrong, I was talking, the sum of your weights, right? So another way of thinking about this is, if I was using that state example, every state you would have an average income value for. You would multiply that by the population of that state. Then once you do that for every single state, you would add all those up. That's what your numerator would be. And then you'll divide by the sum of your weights. Well, if you think about it there, if my weights are the population, right, of every state, when I add those weights up, I should have the entire US population, which would be what I could see in that original data set before it was grouped down to the state level, right? In the original data set, how many observations do I have? Well, I have every working class individual across the United States. So my sum of my weights, or the sum of the populations there, would essentially represent the number of observation in that original data set that I can't see, right? The data set that was then grouped and then given to me, okay? So there's kind of different ways of thinking about this denominator. Usually in practice, we're not told what that number of observations is, so we have to add up the weights to figure out what it is, right? Because we don't have the original data, we just have this group data. Okay? Any questions up to this point about what something means, no tradition? Okay. So I'll come back to this. We'll try to get to some actual numbers here. So the steps are going to be as follows, right? I kind of already said these, but we're going to go through every observation, multiply that group's value for the X variable by its weight, then add all those up, then add the weights together. Now I've got the sum of my weights times the X value as my numerator, sum of the weights is my denominator, divide the one by the other. So those are going to be the steps that kind of line up with this mathematical notation. Let's look at some actual values here. Yeah.
You can go back for a second.
Yeah. Oh, yeah. Comes up. Oh, also, well, I'll let you type this out. So on Canvas, and I'll show you here in just a second what I've been doing or what I will do through the rest of the semester. I put up the current skeleton slides just under the files. So they're like up there with all the, they're not in a folder. And then as we progress week by week, I put the old skeleton slide in the skeleton slide folder, and I put the completed slides in the completed slide folder, or completed lectures. I forget exactly how I named it. But the current skeleton slide that we'll be using every week will always be just under the files tab. I'm not going to put those in a folder, so they always should be right there. All right, so hopefully that was enough time for you to jot that down. I'll show you on Canvas just to show what I'm talking about. So go to the files tab. Here's week 3 lectures. They're just a skeleton version until we get through the week. After the week is over, I'll kind of put these up. And I try to add some names on the completed files so they give you an idea about what the topic was. This will make more sense as we work through more chapters and go through more lectures to be able to identify what weeks we covered certain kind of topics. Okay. All right, let's go back here. Work through an actual exam. All right, see what's the numbers. So if you go out to the BLS, Bureau of Labor Statistics, they have all this income data, but it's all protected. You can't see the actual individual by individual data, but you can get incomes grouped by different characteristics. So I went on there, and you can do it by their racial categories. Obviously, we could break this down to a lot more than 4. The way the BLS does it is you respond, and this is one of the 4 categories that people do. I understand there's a big way to delineate this much more, but just for a simple example, we'll just have these 4 racial categories that the BLS kind of takes. We then kind of have it broken down by gender as well, so we could do kind of 2 different things. We could come up with a weighted mean for males, and we could come up with a weighted mean income for females. So how would I do that? Well, let's think about the males first, and I'll walk through kind of how we do that. Well, right away we can see that each one of these racial categories, right, there's some pretty significant variation in income. Not something we like to see, but that's what exists, right? But we also can see that every single racial category, right, some of them represent a much higher number of people, okay? So when we go through to calculate this mean, we shouldn't simply add the 4 income values up for each racial group and divide by 4. Because then we'd be saying, yeah, that 59,000, that represented 74,000 people. This 60,000 only represented 6,000. We shouldn't be treating these equal, right? This one value represents way more people, right? So we wanted to come up with what the average income was, right? What we would do is go through every group, take their weight, number of people in that group, times their value for the variable X we're interested in, income. So 73,000 times 59,000 plus 11,800 times 38,000 plus 6,000 times 60,000. Kind of do that for every single group. Once we've added those weights times the X values all up, we get our numerator. Now here, I kind of displayed this. I kind of cut out one of the steps for you. If I want the sum of the weights, which should be my denominator, I actually went ahead and did that for us ahead of time, right? Or the Bureau of Labor Statistics did that for us ahead of time. This is a solid table down, okay? So I've got kind of my sum of the weights there. I can go through this process to find the sum of the weights times those X values, and it's as simple as that. Now, if I'm looking at this, which one of these racial groups is going to carry the most weight when I calculate this weighted mean? It's going to be the group that has the highest weight. Well, there's kind of a pretty wide discrepancy here, at least in the BLS data, where that 59,000 is going to carry a lot higher weight when we're calculating the mean, right? Because its weight is higher, right? You can think of it as here. Well, when I'm doing this, I think I might have shown you this before. If I'm dividing everything by the same number, this sum of the X's is really like just add up the X value for every single observation. I can actually rewrite this. If I'm dividing everything by n, it's like multiplying everything by 1 over n. So it's almost like every single observation is being weighted 1 out of the total, equally weighted. When it comes to here, I'll kind of use the numbers because the mathematical notation may not make as much sense. But if I think about here, everything is getting divided by the sum of my weights. So what, about 108,000? So for that first group, right, if I take their weight, and I'm going to kind of abbreviate this to be in the thousands, so it makes my life a little bit easier and saves me a little room, right? For that first group, be 73,000 times 59,000. Divided by that sum of the weights of 108,000. Well, notice here what I'm really saying is 73 out of the 108,000 observations come from this one racial category, right? It's not 1 out of the total now, it's 73,000 out of the total, right? So by using this method, I'm really just kind of weighting each group's value by however many people were in that group out of the total, right? And then for the second group, I would have had what? 11,000 times 38,000. So, oops, sorry. 11,000 times 8,000 divided by that total of the weights, which is 108. Well, that's really like saying 11,000 out of 108. Multiply that by, sorry, I missed a number here. 38,000. There we go. That makes a little more sense. Multiply that 38,000 by, well, there was 11,000 out of the 108,000 people in that group. You don't have to be able to like write this ever. I'm just trying to give you some more insight or just different ways of thinking about it. But the actual process, right? What I would do is go through each group, take a weight, multiply by that group's X value, add them all up. And then here, I actually just wrote this out, even though we had the 108,000 in the chart. If you didn't have it, you would divide by the sum of those weights. Any questions on this before we keep moving? Okay with this right now? So 53,000, I put up the female value as well. It would be the same exact process. You just have different weights and different mean incomes. You can kind of see here, this is, I always, it's sad. I always grab this data and it's always, you very clearly see like racial and gender like differences across income, which, this class isn't about how we address those and fix those, but it's very obvious they exist here, right? We can at least from the data tell that exists. So another way of thinking about this, it might make a little more sense. Maybe we don't get lost too much in the numbers here. So let's say I've got these different categories. I don't know. Say it's a project class, right? So maybe this is 35. Let's do 25, 25, and project is 15. So a really easy common way of using this weighted mean, or where you see it applied a lot, is with grades, right? So the professor told you at the beginning of the semester, there's all these different areas in which you're going to earn points, and each one of them is weighted different, right? The two exams will both count for 25%, the homework's a little bit higher, and then this project, maybe it's not the most extensive project, only 15%. Well, then let's say, I don't know, you get put a lot of time into the homeworks, you don't do quite as well on the first exam, not too bad in none, and I don't know, maybe you do really bad in the project, right? Well, if you simply found the mean, so I guess you can kind of think about this as your score, right, in each category. Well, you don't want to simply add up your 4 scores and divide by 4, right? So that's treating every single category's grade like it's weighted equally, like they're all weighted 25%. Right? What you would actually want to do to calculate your grade in this class is go through, right? Take your weight for that first group, for the 35%, multiply it by whatever your grade was in that category. Then you go to the next one. Okay, I got 25% comes from that exam 1, I got a 70. Then another 25 from exam 2, I got an 80, and then 15 from that project, and I got a 50 in the project. So this is essentially what we were doing here, right? To calculate that weighted mean. We're just taking these weights or the percent that each one of these different categories counts towards your grade and multiplying it by whatever value you had for that variable X or the score in each one of those categories. Now, what did I forget to do here? I still need to divide by the sum of my weights, which if the professor can add up, should always be what? 100%. I mean, unless they kind of do some goofy thing where it's like 110% and everybody has possible for extra credit. But right, it should be that it always ends up to 100%. It's a little bit easier to think about in the context of calculating like a weighted mean for a grade. Just another example, another way to think about it. Any questions up to this point? Questions? All right. So I'm looking at this, just kind of get an idea if we're following along me here. And for me to give you credit for showing up today. So it's not meant to be a difficult question. If we think about what we're doing, I've said it a couple times. So let's say instead of by race and gender, I've got this broken down by region of the country. And I'm calculating this weighted mean. Right? Well, you can see what it's going to be. I'm not asking you to calculate the weighted mean. All I want you to answer with, and I think hopefully, should have it. There we go. A, B, C, or D up there. Right? Which of these regions is going to influence that weighted mean the most? Okay. So think about how we're calculating this weighted mean. You've got the income value of every region. You've got the number of people that are represented in each region. So number of people, kind of like number of people in each racial category, might be our weights. So which one of these regions is going to influence that weighted mean the most? All right, give you a little bit of time. It shouldn't take too long to think about this. Just give you time to get everything out. So which one of these regions, if you're calculating the weighted mean, is going to influence it the most? Just put another few seconds here. If you haven't gotten an answer in, kind of take your best guess. I think there's one more, unless I'm counting wrong. So make sure you get an answer in. I'm going to close it out. 17 of us here today. Okay. So which one of these should be influencing the mean the most? Yeah, south, right? Because what? The weight is the highest. And these weights, all it's really saying, once again, kind of going back to the population idea, the south is 40,000 out of 110. So that should be carrying a lot more weight. It's going to pull the mean towards its value a lot more than 19 out of 110,000. Right? Before, every value was pulling on the mean 1 over n, when we just had a regular mean, right? One extremely large value had just as much influence over the mean as kind of a value near the middle. Well, now the values that have the most influence or pull over the mean are going to be the ones that have the highest weights. For instance, in the grade example, right? Let's say redistribute this so the homeworks are worth 45 and this is only worth 5. Well, if I look at this, I get a 0 here, right? If I calculate my average by like not using the weights, just add these up and divide by 4, I'm going to see a much significantly lower grade. What would that be? So I've got 380, so 240 divided by 4. I've got what? 80 there? Or is that right in my head? No, I can't do it. 60, 80, 80, 240, about 60. Yeah. So if I treated this like a regular mean, I think my grade in the class would be a 60. I add all these values up, I divide by 4. I get 60. But that's not right? Because this category that I got a 0 in, it barely counts for any percent in the class. It's going to have very little pull over my mean. If I instead go through and calculate my weighted mean here, I'm not going to waste time, or I don't know what it is off the top of my head. I can't do math that quick in my head. But it's definitely going to be higher than 60, right? Because I scored pretty high in all 3 of the categories that matter the most, right? The one I scored really bad in didn't have near as much an influence over that mean, so it didn't pull it all the way down to 60. It only pulled it down, a little bit less. Yeah.
Now, since those are percentages, they may not matter. Would you do like 0.25 times 80, or what do you price those things?
Yeah. So in fact, if I instead did this, right?
I meant like down here at the bottom where you
Down here?
Yeah.
Oh, I see what you're saying. I
If
got
that
that. Hold on.
formula does it not?
Yeah, I see what you're saying. So if you want to think about it this way, I usually don't tell people do this just because it's, you often, well, you could do it this way. I guess it's just kind of personal preference. If instead of using the percentages, I wanted to kind of do like I did with the population over there, I could really say 35 over 100 or 0.35 times 90 plus 25 over 100 or 0.25 times 70 and kind of do that for every category. But I'm really mathematically, I'm doing the same thing. I'm just doing an extra step like rearranging things and coming up with a decimal. But yeah, that helps you think about it, easy. And with the grade example, that probably is easier to think about. Then you don't have a denominator to worry about. When it comes to the population, right, it's not as easy to like convert my weight into a nice decimal. I'd have to divide it by the total and might end up having a bunch of decimals. And so generally, we'll kind of use this process where we add them weight times the x value up and then divide by the sum of the weights. Yeah. But yeah, a great example. That makes a lot of sense. Yeah. Any other questions up to this point? Okay with this so far? Okay. So the weighted mean's not too bad. The weighted variance, I think, is a little bit tricky, right? I don't know, maybe not, we'll see, we'll see what we think. So just like I had the sum or the weighted mean was the sum of my weights times the x values divided by the sum of the weights, which we said the sum of the weights we can think of as, that's really the total number of observations in the original data we couldn't see before it was grouped. So we're going to do a very similar thing. So I'm going to try to leave these up here just so we have something to compare to, but erase. So when we were calculating a variance, we said for every observation, we'll go through, take the deviation of that observation's x value from the mean, square it. We're then going to add them all up and then divide by, for a population, kind of our total number of observations. So we said the variance was kind of like this average, right, across every observation, the average deviation from this middle point of the data. Okay. So when we have group data, we can come up with a weighted variance as well. So if I was guessing what I'm doing before with a mean, I'm trying to find the average x value. And if I have group data, really the only thing that changed, remember the denominator really represented the same thing. So the only thing that changed was every single x value, I had to weight it by the number of people, I had the frequency, something like the percent of the grade, whatever my weight was, to account for that, certain x value should have more or less pull over that mean. So the mean is finding the average value, the variance is finding the average deviation. Well, it's the same idea. I'm still going to have a deviation for every single observation. It's just now each one of those deviations is going to carry a different pull, or going to have a different pull on that variance, or influence that variance a little bit more if it represents a higher number of people, a higher percentage of the overall grade. So the only thing difference is we add in, it's the same variance equation that we had before for the population variance, but every deviation from the mean squared gets multiplied by that group's weight, right? Because now we're dealing with group data. Another way of thinking about this, like I said, instead of dividing by the total number of observations, we usually can't see that. We usually have to calculate that, but that's just the sum of whatever our weights are. Okay. So not a whole lot different than what we were doing before. I guess, we've got the weights included now. One thing that is going to look a little different, and I'm not going to try to trick you with this or really overemphasize it with the questions that I ask. But notice I've kind of written up here all the population stuff. Population means population variances. Now, when it comes to the sample variances, finding a sample versus a population weighted mean, no difference, right? But what might be different if I wanted to calculate a sample weighted variance, right? Or a weighted variance that comes from sample data. You remember what we said the difference was between a sample and a population variance before? There was like one thing that we changed. Yeah, the denominator, we divided by n-1, right? So if we have to calculate a weighted sample variance, everything's going to look the same. I guess we have to use slightly different notation, that we're using a sample mean instead of a population mean, but the process to calculate the numerator looks exactly the same. The only difference is here, what we're technically doing is the sum of the weights minus 1, or just like before, we're really saying n-1. But we usually don't know n, we usually have to calculate n by adding up our weights. Okay. So not a whole lot, really following the same kind of principles we work with regular variance when it comes to the difference between the population and the sample. Okay. So what does this look like? I'll walk through one and kind of try to walk through some of the intermediate steps and show you what this would look like if you're doing this by hand. So I went back, I just grabbed the part of the table that was the male income broken down by different racial categories. So if I wanted to calculate this weighted variance, how would I do that? So what I'm going to go through and do is take every single observation's value for X, 59,000, subtract that mean that we came up with earlier, just as a reminder, I think it was 53,000. So 59 minus 53,000, we'll take that deviation, we'll square it, but now the added step is once we have that value, we'll multiply it by 73,000. Write that number down. You can kind of see, like, I'm not going to ask you to do a problem like this on the exam or something. This is, these numbers start to get pretty big when we're dealing with something like populations and, or, so significantly high number of people and income values, because everything's in the tens of thousands, right? So those numbers get pretty big pretty quick. And then I go to the next group, take its income value, 38,000 minus the mean of 53,000, square that deviation, multiply it by the weight of 11,000. Write that number down. Once I do that for every single group, I'll add them all up. That's my numerator. Some of these deviations squared, some of these deviations squared times the weight. And then just like before, I'll divide by the sum of my weights, the variance. Okay. Yeah.
So how are you getting those numbers?
And so you can see if I've got another slide here. So I'll break this down. So what I'm doing here, I'll kind of write this out to give you an idea. So if I was to do this all at once, this is why I kind of create another column. So I'm doing this by hand. It's easier to do this group by group, because otherwise what I should be doing is, and once again, I'm going to write this kind of rounding and just using the first two number, like I imagine this is like 73K, right? 73,000. So I would take that first group's weight, multiply it by that group's X value, which was 59,000, minus the mean of 53,000 squared. I would then have to add to that the next group's weight, which is what? 11,000 times its value for X, 38,000 minus the mean of 53,000 squared. And then add to that the next group weight times 60, which was their value minus the mean of 53,000, square that. And I've got one more, right? So 17,000 times that group's value for X, which is 36. Yeah, 36 minus the mean of 53 squared, and then divided by the sum of all my weights, right? So 73,000 plus 11,000 plus 6,000 plus 17,000. So that's what I say. If I give you an example, I give you something that had smaller values, something like this, it'd be a little bit easier or not as time consuming to enter into your calculator. Also, if you do this all at one time, you can do this in like a, you got like a fairly nice calculator, and I don't have to be that nice. You can do it all in one line. It's just easy to make mistakes with my parentheses. If I forget parentheses and hit square, I accidentally multiply this by this first, I get my order of operations messed up. Doing it all at one time makes it a little bit more likely you're going to make a mistake. If I do this and break this down group by group, write down the intermediate values, it just might be less likely I make a mistake in my calculator. But you can write it all out and do it all in one line. Does that answer your question?
Thank you.
Does that help? Any other questions on this? Yeah.
So like when we do it, will we have to do each one like, because I know this one's just squared, it's similar, just squared. For like, it would have to be like we do the weighted mean, the weighted variance for each thing and then just write them out.
Yeah, so
All the
just
way
like we
down.
wanted to calculate the variance, we first had to have the mean.
Right.
If I want to do a weighted variance, I first have to have the weighted mean. So that 53,000, so you're not pulling it out of nowhere, right? I came from earlier. So we had to calculate that first, then we can calculate the weighted variance.
Okay.
Is that answer your question?
Yeah.
Any other questions? So good, so I want to give like a slightly different way of thinking about this, all right? The weighted variance has a slightly different interpretation than a regular variance. So the regular variance is telling us the average deviation from that middle point, or basically just like the variation that existed in some variable you're interested in. But with group data, the variance actually represents the variation that exists not across every observation, but more of the variation that exists across the groups. So really when we calculate our variance here, so for now, let's just think about the male income. Now we came up with that 94 million with our variance, right? Really large, there's a lot of variation, right? What this is really telling us is not just the variation that exists in income in general, but the variation that exists in income across these racial categories. So it's really telling us like economic injustice, essentially, right? Or the economic inequality that exists across races. So the weighted variance in a way, like, yeah, we can't see the original data, so it's not as useful for just understanding the variation in income in general, but it's more useful in understanding the variation that exists due to this grouped characteristic. The group characteristic we had here was race. So here, I've got a much higher variance for male income across these racial groups than I do for females, right? So what that's telling me is that the racial inequities that exist in income for males it's much more penalized, right? Or there's a much greater variation in male income across races than there is female variation across races. Which, once again, depressing stuff. But this is the data, right? This is what it is. This is how we can then go forward and try to make, policy changes. Or policy suggestions, changes. So same kind of idea. I broke this down by region. It looks like the variation that exists in male income across regions of the country is also greater than the variation that exists in female income across regions of the country, right? So the fact that we have two characteristics that looking like, female income varies a little bit less, maybe just overall there is a little bit less variation in female income, right? It doesn't matter what characteristic, these other characteristics don't impact female income near as much as male income. I really don't know what's going on with this region of the country one. The racial one, I could, this kind of lines up with a lot of previous research. The region of the country one, it might be that certain types of jobs are more likely in different regions of the country, and male and females may be selected into those jobs, but at the very least, we can at least measure that variation, right? And it's now no longer just the variation that exists in income, it's the variation in income across regions or across racial categories. Okay. Questions here? So, push this a little bit further. And I have two races. So, one thing that we've done before is look something like this, which is sometimes the original data is put into a histogram, right? There's this huge data set, and then we, break it down into these different bins. We calculate the number of observations in each bin, and we had something like we did this in Excel, right, before we graphed it. So this was like some product, and they had 60 and 65 people. If we have these up, we'll see if I remember right in a second. And then they had their satisfaction rating of this product. They then, instead of showing every single person, they said there was 25 people who responded with either a 42, 43, or 44. And there was 2 people who responded to either 48, 49, or 50. So we can't see the original data. All we can see is this grouped histogram data. Right? But we can still calculate a mean. We can still calculate a variance. Okay? So if I was just looking at this, what would you guess the mean is of this data? Well, which of these groups has the most or represents the most people? The rating of 42 to 44, right? Now, the other groups on either side of that are kind of equally as far away from that point, right? There's an equal number of people. Well, not equal, but close, right? Fairly equal on either side. And then even the categories that are a little bit further from that, well, there's not hardly any people in those, right? So it looks like it's a pretty symmetrical kind of group data around that middle category. We can actually go ahead and compute what this is, we don't have to just guess, right? So I guess the problem becomes, if we were going to do a weighted mean, so I'll write up what we had before. Now our weights are going to be what? So what would I use in if I wanted the average satisfaction rating here, what would my weights be? Your average amount. So you're thinking about the X value. So you're all on the right track, right? If I'm looking at the satisfaction rating, that's the variable I care about. That's what I want to find the weighted mean of. Okay? So my X variable is going to be that satisfaction rating. The problem is, well, what number do I use? There's several numbers in this range. If we had a different example, maybe where I was counting between 50 and 60. Well, there's a lot of numbers in between. So what we'll do if we have this histogram data, it's in bins, we're going to take weights and multiply them by the median of whatever that group, what that group's values are. So in this case, the values we would use would be 37, 40, 43, 46, 49. So if we have this histogram data where we've got frequencies by these different kind of bins or kind of range of values, we'll use the midpoint of each one of those bins. We'll then multiply that midpoint by the weights. Well, what are our weights here? It's going to be slightly different notation. It really doesn't matter. We could keep writing W if we wanted to. The weights are just frequencies now. With histogram data, it's always going to be frequencies. Okay. So yeah, the notation changes, but we're really doing the same thing. We're taking the weight, just now that weight is a frequency, and we don't have one X value. We have to figure out what that value is by taking the midpoint of some range of values. When I say midpoint, the median, right? The middle value. And then similarly, we'll divide by the sum of the weights. The sum of the weights are now frequencies, right? But it's really the same process. Well, the only wrinkle here is that we have to use the midpoint, and then the weights are now called frequencies, but they're really, those two words are interchangeable. So if I go through, I'll come back to the variance in just a second. How would I calculate that mean? Well, the very first group, I've got midpoint of, or median of 37. 37 times 4 is 148. And then go to the next group. I take their median of 40 times 15, their value is 600. I do that for every single observation, right? And then I add them all up, right? That summation sign says, do this, right? Take the frequency times the median for each group, and then add them all up. Once I add them all up, that's my numerator. I still have one last step, which is divide by the sum of those frequencies, or we could write that as the total number of observations, that original data we can't see, like the data before it was put into these bins. So you can kind of take some of the frequencies or n if you're given them, right? Here we weren't given n, we can compute that by adding up the frequencies, but probably gonna have to do an added step in most cases. You're not just gonna be given what that original sample size was. You can figure out what it was by adding up the frequencies. Okay. Questions on that? Does that make sense in this? I want to move on before we're okay with this. Should look pretty similar to what we were just doing. Right? So we've got our weighted mean, these histograms. Oops, let me go back. Thought that there we go. I was gonna say, I thought I had it up there. So our sample variance, I had this up earlier, but it's going to be the same thing we had before. It's just instead of X values, we're using the median of our bins. That becomes our X value. Our weights are now frequencies. And we can write this denominator one of two ways. We can think about it as n-1, or this helps. I'll write it out in a slightly different way. Actually, I can use X bar here, don't I? Right, instead of n-1, we can think about what's n. Oh, n was just the sum of our frequencies, or the sum of our weights. So kind of two different ways of thinking about this. So if I wanted to do that for this satisfaction rating variable, what I'd go through and do is say, okay, look, my mean, if I remember, was what? 43, exactly. The numbers just more down. This is an example to make it a little bit easier. So I'll go to that first group. In fact, I'll write this as I'm saying. If you want to kind of follow this, talk through it, I'll actually have it written down too if you want to take notes on this. So I'll go through that first group, right? What's its median? Or what's its midpoint? 37. Subtract that mean of 43, square it, and then you still need to do what? Multiply by the frequency of that group. Then I'll go to the next group. Well, what's its frequency? There was 15 people. The median's 40 minus the mean of 43. But I have to have that deviation squared first and then multiply by the weight. Then I go to the next group. What? 19 times 46 minus 43 squared. Which my board is a little bit wider, so I can have this all on one line. Oops. But here we are. That's that one, 49. And I still need to divide by the sum of my frequencies. I forgot a category, didn't I? Yeah. Yeah, I forgot. So here. Sorry about that.
37,
43, there we go. Sorry, so you can add that in down here if you want. I didn't want to trip you up. I should have done that in order. I was looking and I skipped the group 1X. There should also be a what? 25 plus 19 is 2. Okay. Now here, my mistake is a teachable moment. Why did it really not matter that I forgot that group?
Because 43 minus 43 is.
It's 0, right? Remember, this variance, before we even did weighted variance, is the average deviation from that middle point. Well, there are going to be some observations that are exactly equal to mean. They're evidence of no variation. In this situation, we actually had a group that did not deviate from the mean. And in fact, it was the most common group. So it's going to be pretty strong evidence that there's not a lot of variation in this data, right? So that 0, right, is not going to add anything to that numerator. So it's going to make sure that my numerator is pretty close to 0. Right? It's not adding anything, and 0 divided by anything is 0. Right? So it's really going to kind of keep my variance low there. Okay?
That's only if your midpoint is your mean though, isn't it?
Yes.
Because
It would have to be, exactly. If it's anything other than my mean, it's gonna add something to the variance, right? Yeah, it just happened to be in this situation. Now, we had one group that was exactly equal to that mean. Pretty uncommon in practice, but here, it worked out. Other questions? I want to stay here. Oh, actually, I had one more thing that I needed to do in this denominator. I didn't complete it. So I got lost up in the numbers, right? So this was the sum of my frequencies. If this was sample data that was put into this histogram, I need to divide this by the sum of my frequencies minus 1. There's still one more step I have to do if I have sample data, which I believe is, yeah, how we were treating this satisfaction rating data. Right? We just had 65 people. There's a lot more people that bought this product, right? We just had a sample. I think I have it up there, right? 65 minus 1.
So the denominator is the sum of all of them together. It's not the mean.
Yep. So that denominator, it's actually the denominator for, if it was population data, the denominator for the mean and for the variance would be the same, the sum of the weights. The fact this is sample data, our mean, we're still dividing by the total number of observations or the sum of the frequencies, but for our variance, we're going to divide by the total number of observations minus 1 or the sum of the frequencies minus 1. Okay. So that's my variance. See if we can remember what we talked about last week. It's a long weekend. Maybe some activities that helped us forget. How do I find the standard deviation? That's my variance. One more step. Take the square root, right? So, hopefully that becomes old hat. I'll probably ask you an annoying amount of times for that, but I want to make sure we kind of hammer that down, because once we get to things like confidence intervals, like we need to be able to do that in this like stagnation. All right. So, so that quite a bit of time. So let's go through this. If I have time at the end, I might show you another example, or I might show you a little bit in Excel with weighted means and variances, but it's not going to help you much for homework. So I'm going to punt on it for right now and maybe just show it to you in practice and maybe a quicker way to calculate this down the road. So we'll jump topics. So for right now, which is the next thing that we want to talk about, is percentiles. So this is interesting in and of itself, but it also allows me to talk about something that I know you'll see in some of your other courses, especially marketing. I think uses them a lot. And some of your upper level courses, this might show up. So before I even go into this, I know that colleges, I guess, just don't care about the SAT and ACT scores anymore. But it's assuming that some of you took them, right? They tell you what percentile you're in. Right. So if they told you that you're in the 90th percentile, whatever your score was, what were they really saying? That you did well, or that you did better than 90% of the other people, right? So why does this matter? Well, pretty real application of this is what do you think probably happened to ACT scores overall or SAT scores overall during the pandemic for high school students? They got lower, right? Well, just because they're lower, I still want to know who are the better students, right? And I can look at the actual number, but if I'm comparing across time, like I have to realize that every year students encounter a different set of characteristics. So I might want to have like a relative measure. This percentile is a relative measure. Like you said, if you're in the 90th percentile, you're better than 90% of the other people who took the SAT or ACT, whichever one we're looking at. In fact, I had a class once in college. I think that he told us our percentiles because I'm pretty sure the mean ended up being like a 30 something. It was like some linear algebra course I took that like, I'm pretty sure no one understood half the course, right? So you're just graded relative to how everybody else did. Everybody failed, right? But you were kind of given a grade based off of how well you did relative to everyone else. Anyways, so we got this percentile. 90th percentile is really saying whatever percentile you're told, you're better than that percent of the other people, or in data set terminology, better than 90% or higher than 90% of the other observations, right? If they had all the SAT score data in this, some database, they're telling you you were higher than 90% of the other observations, or said differently, if I'm in the 90th percentile, my score was worse than 10% of the other observations, right? Or 100 minus whatever that percentile was. So another way, place you might have seen these before, and like I said, I'm trying to set this up. I'm not going to ask you to like give me the verbatim definition of a percentile ever, but this is the general idea, right? So you may have seen these, something like this, like this is doctor's charts. I feel like maybe one more point in time, you might have seen something like this. It tells you that, at the age of 15, if you were 6 feet tall, right, you'd be in about the 5th percentile, right? Or if you were 18 and you were what? I don't know, 70 inches tall, you'd be somewhere between the 50th and 75th percentile. So how are they coming up with these values? Well, basically, doctors record all this information. They might share it with like the American Medical Association. They look at all this data, and there's a process for coming up with these values. So the way that they do this is they arrange the data from smallest to largest. Okay? So once you have it from smallest to largest, I'll give you a way to think about it, and it's not technically a perfect explanation, but it helps get the idea behind how we're going to do this, right? So let's say I had 100 people, right? And they've all got different heights. I don't know, 62, 74, etc. Okay? If I want to know what height, or actually, I should have, if I arrange these from smallest to largest, I probably should have started with like smaller values, right? And it goes up. If I want the value that is the 90th percentile, so what height would be the 90th percentile here? I would go down to the 90th position, and then whatever height was in that 90th position, well, that's higher than 90% of the observations, lower than 10%. Right? Kind of like with our SAT, better than, well, to be taller or shorter is not necessarily better than, but like in the idea of the SAT, better than 90%, worse than 10%. Okay? So the reason why that doesn't quite work out is once I take out one observation, I've really only got 99 left. So it's not perfectly 90-10 split. So what we'll actually do is use this equation that accounts for that, right? And after I've arranged this data to find the position, and also we're not always going to have an easy to think about number of observations like 100, right? If I had 623 observations, well, then what's the 90th percentile? What position do I go to there? It's hard to think about. We have this equation that will tell us what position. We plug in whatever percentile we're interested in finding. We plug in the number of observations that we have in our data, and it returns to us the position that has that percentile value. So if it returned to us the position of 90, we go to the 90th position, look up that height, and that would be our 90th percentile. Okay.
L is the position.
Yep, so you can think about it. L is the location of this position, or sorry, the location of that percentile. Writing P subscript P, a little bit, so the location of this percentile. So once we have that value, if it's an integer, pretty easy, right? If we get 90, we go down to the 90th position, we just grab that value. That's pretty easy. But what if we get like 3.9, or sorry, 3.42? Well, then we have to do something called interpolation, right? So I'll walk through kind of some interpolation examples. It's not too bad. There's one little thing that can be tricky with it, but I'll show you some different examples. And there's actually a lot of times during the semester we could do interpolation, and I will punt on it, but I at least want to introduce the idea here so we can calculate these percentiles because they don't have some usefulness. And then I can always mention it later on in the course. So the way that we'll do some interpolation, right, when we have these more difficult examples, will be something like this. So let's say I had 10 metal funds. Not that interested in the example, but you know, think about these as mutual funds or anything else. These are just have some nice values for us, right? So I arranged them from smallest to largest, right? This one had a negative, I think this was actually changed in value. So negative 56 on the 76, right? So I want to first locate the position of the 25th percentile. So how am I going to do that? I go back to that formula, right? I plug in my value of 10 for my sample size, I have 10 of the funds. I wanted the 25th percentile, right? I get 2.75. So what's the problem? There is no 2.75th position, right? There is a second and a third position. So how can I find what that value is? Well, if I want to be lazy, I might say, oh, let's take the average of these two values, right? I'll take an average of the value in the second and third position because I got 2.75. But what that's ignoring is that 2.75 is going to be a little bit closer to the value in the third position. So I'm a little bit closer to that value in the third position of 8, then maybe that 8 should be carrying a higher weight than the value in the position of 2, right? Or that negative 7. So this is going to be basically a weighted mean. Interpolation is just a unique application of the weighted mean. How are we going to figure out what our weights are? Whatever your decimal is. So if I get that the position is 2.75, the decimal tells me my weight, my first weight. And then my other weight will be whatever gets me up to 1, right? So here that would be 0.25, okay? So we're going to do the sum of our weights times the x values divided by the sum of the weights. So all we're doing with interpolation is really finding a weighted mean. So here's my two weights. I know I'm in between the second and third position, so I should be using negative 7.34 and 8.09. Which one gets the higher weight? Well, what position am I closer to? 3. So that value is going to get the higher weight. The other value, do I remember these right? Yeah, the other value is the lower weight. I then divide by the sum of my weights. But the process that I told you for identifying the weights, look at the decimal, then whatever gets you up to 1. What are the sum of my weights always going to be? 1. So I can essentially ignore the denominator when it comes to interpolation. It's actually an easier application of a weighted mean. So if I do this, hopefully I get a value that's a little closer to the number in the third position than the number in the second. And sure enough, I did, right? 4 is closer to 8, and this is negative 7. So based off of this data, the 25th percentile for all metal funds, even if I only had a small sample here, I can calculate the percentile for maybe a larger data set. Any questions at this point? I'm going to throw another little wrinkle in it that might make it a little bit tougher. Yeah.
So every time there's a decimal, that's what we'll have to do for the percentile.
Yep, anytime there's a decimal for the position, you'll use that decimal as your first weight, your second weight, whatever will get you up to 1, and then identify what position am I closer to. That value gets the higher weight. In fact, I'll show you one. I don't know if I have it on here. So I think I have this as an example that we can work through, but let me go back here and make sure. Okay, so this is a good one. I'm not going to ask you guys to do this one by hand because I want to more so use it as like a kind of showing you how you'd have to approach it. So let's say I wanted the 75th percentile. Right? So what would the position be? Right? How would I find that position? So we said formula for the position was n plus 1 times p over 100. So if I want that 75th position, I've got what? 10 plus 1 times 75 over 100. Right? So if I had to guess around what position that's going to be, I'm going to guess probably somewhere around the 7th or 8th position. Right? So I'm guessing that my values are probably going to be kind of up here somewhere. So negative 3.5 probably doesn't make a lot of right. Negative 3.5 would be higher than 2 of the observations, less than 8 of them, right? So that doesn't make any sense for the 75th percentile, right? How can you be better than 75% of the observations when I'm actually looking here is negative 3 would only be greater than 2 out of 10. It doesn't match up. Right? Now the other ones I can kind of think through, right? 55.5, well that would be here. Okay, well that's worse than 2 out of 10 and better than 8 out of 10. So probably pretty close to that 75th percentile. Same kind of idea though, 51 and 47 are kind of in that same range. So I probably can't just like guess. I actually have to work through this problem, right? But I could rule C out right away. It makes no sense, right? If I'm trying to find the 75th position or percentile. So I go ahead and I plug this in and I get a position of 8.25. So here's where the slides have this, but I want to walk through this so people don't focus too much in here and kind of see what I'm doing right here. So what's my first weight? How do I find my first weight? I look at that position of 8.25. I use the decimal, right? What's my second weight? Whatever gets me up to 1. Now here's where if I have a value from that position that's like 8.2, 8.3, 8.4, something below 0.5, it is a little bit different because I can identify my weights, right? And I know that I'm in between the 8th and the 9th position. But now I have to determine, okay, but which of these values gets the higher weight? For 8.25, what position am I actually closer to? 8th position. So the value in the 8th position doesn't get weighted by 0.25, it gets the higher weight, right? Whatever position I'm closer to, in this case, the 8th position, that value of 43 gets multiplied by the higher weight. So before, when I identified the weight, I was like, well, I know that that higher weight goes with whatever position I was close to. I just have to use my brain a little. It's not like I can just write the weights down and then plug the numbers down in order. I have to stop and think, okay, I've identified my 2 weights. The value that gets the higher weight is whatever position I'm closer to. And when I have 8.25, I'm really saying I'm closer to that 8th position. And then that means 0.25, what the 9th position value would get multiplied by that.
So could you think of it as like, since 0.75 is obviously bigger than 0.25, could you just think of it as you put it close to the bigger number, like the bigger is with the smaller and the smaller is with the bigger? Is that confusing?
No, I know what you're saying. No, right? Because in this case, what actually, well, probably if I write better. What actually happened here? The higher value actually gets the lower weight.
Okay.
Because that higher value was in a position I was further from. The higher, yeah. So this is why what you're saying,
Yeah, I think
always works here, right? That's always easier to think about. Like the higher value is always going to get the higher weight if my position is above 0.5. It kind of is counterintuitive when you have a position that goes below 0.5, like we did here, because then when I'm identifying the weights, it's actually like reversed, right? But the universal thing that will work is identify your 2 weights, and whichever position you're closer to, take that value, multiply it by the larger weight. Doesn't matter if that value is smaller or larger than the other, it's going to get the higher weight because I'm closer to that position. Good question.
Thank you.
Any other questions before we keep moving here? So what's going to be a really easy, so other than an integer of like 8 or 7 or 6, those ones will be really easy, right? came up with, 8 here, I go, oh, okay, that's the 70th percentile, right? The value of the division. What's another really easy value? If I came up with a position that had a decimal associated with it, what's a really easy interpolation value that you can see this decimal be? 0.5, right? Because then I've got 0.5 and 0.5 is my weights. All I'm really doing, I'm equally weighting each number. I could just find the mean, right? So if I get 0.5, it's a real easy interpolation problem. It doesn't often happen, but it could. So, all right. You can identify these percentiles. So this is what I said you might see show up in some other classes. Maybe you've already seen this before. So what I'm going to do is come up with these 3 what we call quartiles. The 25th, the 50th, and the 75th percentile. That's my first, second, and third quartile. Think about it, basically, it's like dividing my data into quarters. Right? So what we're going to do is create what we call a box and whisker plot. Right? Maybe you've heard this before. So what we're going to do is graph the first and third quartile first. Right? So this might be something like, I don't know, 60 and 220 down here. And then I'm going to find my second quartile. Say this is 50, just to make this a little bit more interesting of an example. And I'll kind of draw my second quartile in the middle of that box. Right? This is the box part of my box and whiskers plot. Now, what this tells me here is that the upper end of the distribution, right, is a little bit closer to the median than the lower. So I might have like a lower, kind of longer left tail. Now, I'm not going to expect you to do that interpretation, but once you see this pop in your classes, this is often what the box and whisker plot is used for. The box portion tells you something about the skew of the data. That's not what I'm going to focus on here, but you can't get that. So the next thing that we're going to do is come up with the interquartile range and then use that to create an upper and lower limit. And I'll describe what the purpose of that upper and lower limit is in just a second. But it's not too bad. Once we have this 75th, 50th, and 25th percentile, finding the interquartile range is just taking that third quartile and subtracting the first. So the reason why we do this is, if you think about it, if I'm looking at some like income, the range is 0 to Jeff Bezos, right? Or whoever, I don't know, whoever's everyone's richest now, right? But the majority of the data, the majority of it is like within this box, within the first and third quartile, right? The extreme outliers will be way outside of it, but the majority is in between that first and that third quartile. So that's what we'll call our interquartile range. Right? So here that would be what? 60 minus 20, just to have some values to go with it. Okay. Now from here, we're basically going to take 1.5 times that interquartile range, plot that point down here to create my lower limit whisker, and then go up here, plot, add 1.5 times the interquartile range to get my upper limit or my upper whisker. So here, if I took that third quartile, added 1.5 times the interquartile range, I'm getting what? 60 plus 1.5 times 40. So this should be, if I'm doing math in my head correct, 120. And then to get this lower limit, I'm taking the first quartile, right, where my box stops down here, and subtracting 1.5 times that interquartile range. So if we plug our values in here, 20 minus 1.5 times 40, what? Negative 40. I'm doing that math. Right. So it's not that difficult of a process. It's pretty basic math. What's the purpose of it, right? So the reason why we do this is we say, okay, look, we know that the majority of the data is somewhere in here. We'll even go like err on the side of caution. We won't simply add the middle range to get our upper and lower limit. We'll add 1.5 times that. So that's going to be our upper and lower limit. If anything in the data is outside of this range, so if we see an observation that's 130, or we see an observation that's negative 50, right? what we can say is it's outside of our upper and lower limit. Statistically, we can get rid of that observation as an outlier. Right, we have identified it as an outlier, it's outside of our upper and lower limit, and we now have statistical justification for excluding it from our data. So I'll give you an example of like when this applies. I did some alcohol use data for a project, and it was like the number of days that someone uses alcohol every month, and there was a 60. Well, now I know that makes no sense, right? But to just start throwing out observations, you're not supposed to do that. So with survey data, you can get people responding in crazy ways, right? Well, when I looked at the rest of the data and I built something like this, the upper limit was like something far below 30. So someone who responds with 60 days a month, which makes no sense to begin with, I can statistically justify getting rid of that from my data set. So this process for identifying these outliers is what we call the Q-test, right? So, you know, you might see this pop up in other classes, especially when you're dealing with survey data, and you might have some extreme values pop up and you're like, man, these are really influencing my mean, or they're really influencing some of the statistics I'm coming up with. So I'll use this Q-test, identify them as an outlier, and get rid of them from the data. So kind of great mean that goes with that. Please don't reject me as an outlier because you were the Q-test. Terrible stats joke, but I'll use them throughout the semester. So this is how you would create those box and whisker plots. Kind of where we'll pick up, I think, on Monday, is I'll go over how we start looking at not just one variable, but the relationship between two variables. And we have a couple statistics that we'll talk about calculating that'll help you out in like the last 4 questions of that Connect assignment. You can do parts of those last 4 questions already, but when it comes to things like the covariance or the correlation coefficients, we haven't talked about those yet. All right, so I'll push that due date for the Connect assignment to be the end of the day next Wednesday, right? We'll definitely finish talking through everything on Wednesday. I would highly suggest working as far through the Connect homework as you can this week, and definitely the Excel homework as well. Finish up early next week on Monday if you have to. Then after Monday's class, kind of finish up the Connect before the end of the day on Wednesday. Okay. Any questions? Yes.
Do you think the due date of the Connect assignment?
I think I originally had it set maybe to be at the end of the week. I knew that we weren't going to quite cover the covariant stuff. I thought we might get there today. I could probably rush through a good majority of it in time, but there's no sense in like I want you guys to really understand it. So I pushed the due date. I'll even push it forward to next Wednesday. So focus on that Excel assignment first this week, and then kind of work this through as much of the Connect as you can until after class on Monday. Yep.
For like our tests and stuff that we have, we need to keep like the formulas and stuff, or do we have to?
Yeah, so that's a good question.
Because I know it's a lot.
On the exams, before we get there, I will put up a formula sheet. In fact, I'll get it up on Canvas. You're not going to understand half of it yet, but what we've covered through, you can kind of see it'll all be on a formula sheet that you can use on the exam, and also get some practice exams up here before we get too close to that date. Yep. All right, I will see you guys on Monday.